Now it would probably be a good idea to open the window and let this computer cool off a little bit before recording this, but then that would let the sound of the construction in even more than it is already. So this might be a little choppy, but this isn't too hard of a problem, so this should not be an issue. So anyways, this is kind of a peculiar problem because we have to prove that the union of any number of open sets is open. And it's peculiar because when you study general point set topology, which should be coming not too long after this textbook, or maybe even at the same time as this textbook in a typical math course path. When you study topology, topology is defined as a collection of open sets, and open sets are defined such that the arbitrary unions of open sets are open, finite intersections of open sets are open, and then you've got the empty set is open and the whole space is open. So that's how you define a topology on the collection of subsets of a space. And so here we're proving that the union of any number of open sets is open. What we're doing is we're saying, well, in Spivak he defined open sets to be, well, either open intervals on the real line or otherwise just open rectangles. And we took that as our definition, and now we're proving that it's closed under arbitrary unions and finite intersections. However, typically the more rigorous way to do this, there's the construction. The more rigorous way to do this would be to say, hey, this is the general notion of what a topology is. And then in Rn, you can get a particular topology by considering open rectangles. And before you can even call these sets open, you have to claim that these sets, these rectangles, form a topology, meaning you have to check that they are closed under arbitrary unions, finite intersections, blah, blah, blah. So we're kind of doing it backwards. We're calling things open sets and then proving these properties about them. Whereas it'd be better to be like, okay, these are the properties that open sets have in general. And then in this particular case of Rn, check that this particular collection of subsets gives you a topology. But I guess the nice thing about this is that it's a little more like you don't have to go into like defining an abstract notion of topology. You can just kind of get your hands on this real quickly, because you can kind of see what these open sets look like. They look like rectangles. Whereas in general topologies, it's not always clear how to visualize these open sets. So I guess this is a little easier, but once you have a little more background, it becomes a little more cumbersome. But anyways, it's just a little spiel before getting into this. So let UI be open rectangles, or we're just going to call them open sets. And let U equal the union over all I of UI. Now this I I'm not specifying, like I technically should say like I in some indexing set A, and this would be the union over all I in A of UI. And again, sorry for the handwriting, my wrist is still sprained, but anyways, it's a little strange here because typically this would lead you to believe, oh, A would just be either like the natural numbers or something like that, but A here can be any sort of collection. It doesn't have to be countable. It's just any arbitrary collection. So anyways, let U equal the union of these. So we want to prove that this is open. So let X be in U. Well then, if x is in u, then there must be some I such that x is in ui. So ui is an open rectangle such that x is in ui, which is obviously a subset of u, since u is a union of ui and a whole bunch of other things, potentially. This holds, or rather, such ui exists for all x, and thus u is open. And there we go. That's all we have to do, because every point is contained in an open set, which is contained in the set in question, and that is that's how we confirm that sets are open. So anyway, so I guess technically here, let me think about this. So I guess that these UIs need not be rectangles now that I really think about it. But I guess it doesn't matter. It doesn't, I mean, yeah, this is there's a lot of topology stuff going on in the background here, and Spivak's introducing a portion of it, and so it's hard. It's a little difficult to think like, okay, what things that I'm used to using can I use, and what things that I'm used to using can I not use? And I think this is all valid. It doesn't need to be open rectangles here. All these need to be our open sets. But for every point, there's an open set containing that point, which is contained in the entire set. And so that's what it means for this bigger set to be open. So anyways, let's go on to proving that the intersection of sets are open. So let me just check here real quick. Okay, yeah, I just want to make sure that I don't have anything mixed up in the definitions. So for the next part, let U1 and U2 be open. Then let X be contained in this intersection. And let A let A be a rectangle, A1, B1, all the way up to AN, BN. Let's see here, we're not done. And so here I called this C so that we can go C1, D1, all the way up through CN, DN, such that X is in A, which is contained in U1, and X is contained in C, which is contained in U2. And this is possible because U1 and U2 are open sets, and so we have open sets A and C that can be fit inside there. And without loss of generality, we can take these sets A and C to be rectangles. This is the part where I'm thinking if there's more that needs to be said here. What this comes down to is the fact that open rectangles are a base for the topology on our end, but that might be a little bit beyond what's going on here, but only slightly, I think. Anyways, I think this should be sufficient enough of a justification that you can just say, oh, we can just take A and C to be rectangles. then A intersects C is an open rectangle containing X. And why is this? For the ith, I'm just going to call it component, but if you look at, like if you were to slice this thing up, the ith component of A intersects C is the max from AI CI, and then the min of BI DI. That's because if you imagine like two intervals like this and they're open, and you were to take the intersection of them, like we know they overlap because they have X in them. And so when you overlap them, you're going to get this smaller interval. And so what's the left endpoint going to be? Well, here we have A on the left and here we have C on the left, so it's going to be whichever of these two is bigger. And likewise on the right, we've got B here on top and then D here on bottom, and so when you intersect them, you're going to get whichever one is the leftmost. So there you go. So A intersects C is an open rectangle, and A intersects C contains X and is contained in U intersect U1. Such an A intersects C exists for all X in this set, and so U1 intersect U2 is open. Here, how much do I need to scroll down? Not very much, but here. By induction, let's see here. So you prove that the intersection of, so by induction, the intersection of finitely many open sets is open. And I guess this is a little early on in one's mathematical career, so I guess it should be important to actually write out this exercise. Like, why is it clear that the intersection of finitely many open sets is finite, following from just, well, we just proved it for 2. But basically, the proof is the exact same. You just don't really need to change anything in the induction proof. You just do the base case, but you change a few of the things around. Like, basically what you would do is you would say, oh, well, instead of looking, like if you were looking at U1 intersect all the way up through UN, then by the inductive step, you know that U1 through UN minus 1, if you were to just intersect those n minus 1 open sets, then that would be open. And so you can put an open rectangle in there. So these ones would give you an open rectangle, let's call it A. And then this one you can get an open rectangle, let's call it B. And then you just do the same thing you did in the base case. You can intersect those two, and you would get another open set. And so really, I guess, while this doesn't really show all of the details in full, a lot of times this is sufficient for giving an inductive proof, because what you've done is you've shown all of the main ideas and all of the main tools that are needed. So now we want a counterexample we want infinite intersection of open sets to not be open. So there's a bunch of different examples you can come up with, but here is one. The intersection of all I and n of 0, 1 plus 1 over I. Well, this is a countable intersection of open sets. But what is this equal to? Well, if you have any number that's greater than 1, then it won't be contained in so given any a greater than 1, you can find an n a natural number such that 1 over n is strictly less than a. And so the interval from 0 to 1 plus 1 over n will not contain the point a, and so a will not be in this intersection. And this holds for every single a greater than 1, and so what you're going to get is this half-open interval. And this is not open. And that's because if you choose any rectangle containing the point 1, it's going to have to go to the right of 1 a little bit. And if once it goes to the right of 1, it's no longer contained in this half-open interval. And so this is a counterexample to show why this is not closed under infinite intersections. And in fact, this is countably many infinite, which is, I guess, in some sense the smallest infinite that there is. So there you go. This completes the proof.